Welcome to Space News from the Electric Universe, brought to you by the Thunderbolts project at thunderbolts.info. The Electric Universe theory has laid the foundations for an entirely new understanding of planetary geology. For decades, experimentalists using electrical discharges have reproduced many familiar geological features, including types of crater forms that have long proved puzzling to standard geology. These experiments may provide clues to past events that the scientific mainstream has never entertained. High-energy electrical discharges at an interplanetary scale. Is it possible to integrate these new possibilities into a geology that also includes standard geological processes? In this episode, our guest Barry Setterfield, the astronomer at the New Hope Observatory in Grants Pass, Oregon, outlines a number of guidelines for assessing whether craters on planets, moons, and other bodies were created by impacts or by electrical discharge machining.
Okay, well, I was teaching astronomy at the time, and the issue of the origin of craters on astronomical objects of all sizes had come up, and we needed to resolve this issue with the students. For example, in the days before the Apollo moon landings, and even for some time after, there's a strong body of opinion which held that all such craters were the result of volcanism. And that idea died slowly. It was replaced by the idea that all craters are the result of impact. But then the results of electrical experiments became available, which solved problems that neither impact nor volcanism could. And I needed to do some cratering experiments to distinguish between the various types of craters and then present these results to my students. Volcanism usually has craters at the tops of mountains. Unlike the moon and planets, the crater bottoms there go below the level of the surrounding plains. The volcanic craters that look like those on the moon are called calderas, but calderas are only circular and at ground level if the collapse to a depression follows the first major volcanic outburst, and that's rather rare. The basic rule of thumb is that the rim material of lunar craters will approximately fill the pit. This is not usually the case of volcanic calderas, which have a different profile. However, it is the case with these other two methods. Now, Venus is covered with 1,600 volcanoes, mainly the shield type of volcano, which is similar to those in Hawaii, but they're more broad and flat. Radar surveys also show that Venus has about 1,000 craters, similar to the Moon and Mercury and Mars. And these have a different character, and so they're formed by different processes. In addition, the proliferation of craters on very small asteroids and dwarf planets rules out volcanism as being the origin for those craters. You can't have a volcanic hot magma centered to such a small body. It doesn't work. So there are features of both impact-based and electrically based crater formation that correspond with what we see on objects in our solar system. Both methods of crater formation describe some, but not all of the features that we observe. From the experimental analyses that I have done, it seems that we have a mix of both electrical and impact-based craters. And these experiments seem to allow us to determine whether or not a particular crater may have formed by impact or by electrical discharge machining, EDM. Craters can be formed by the impact of some solid body, such as an asteroid or a meteorite, and as that body hits a planetary surface, its velocity can range up to 45 miles per second, which is pretty fast. This can be simulated in a lab experimentally. Since real impacts will smash any material from soft pumice to alloy steel, the material that we use in the lab should have no tensile strength. Now, there is such a material, and it's dust. And for practical reasons, we use cement dust. It comes in uniform quality. And so we have a layer of cement dust about 6 inches thick in a large box or a pan. And the meteorite is then a spoonful of slightly compressed cement dust dropped from a height of about 4 feet. The resulting craters have a striking resemblance to lunar craters generally. In the case of an actual impact, as the impactor penetrates the surface, it pushes ahead of it an increasingly large plug of matter that becomes intensely hot and under high pressure. Eventually, the pressures involved reach something like 200,000 atmosphere, and this stops the plug of intensely hot material and then a massive explosion occurs. It doesn't matter what direction the meteorite comes from, the focus of the explosion forms a circular crater around that. The pressures involved form what is called shock quartz in the plug, which can't be formed by volcanic processes. As the crater forms, the horizontal strata at the rim of the crater becomes upturned and folded back on itself by the explosion. So the strata will actually fold back in the reverse order like a mirror image. These mirror image strata sit beneath the debris layer near the rim and is an expected feature of many impact craters. The impact craters can exhibit rays made up of powdered material thrown out from the explosion center. These rays are bilaterally symmetrical, mirror image that is, not radially symmetrical, and this is typical of explosion pits on Earth. The best example on the moon of the ray is the ray system of the crater Tycho. Impact craters often have radial ridges of material excavated from the explosion as well. And in addition, there'll be central peaks formed for craters within a specific size range. But that range depends on the gravitational pull of the planet or the moon that's formed on. Lesser gravity means larger craters for explosions of the same energy. Craters from impact will often have terraced walls as the ring wall slumps along the tangential fault lines set up by the explosion. There's also a set of radial fault lines going away from the crater center for the same reason. The craters, the terraces, the central peaks, the rays, and the radiating ridges can be reproduced in the lab experiment. So can multiple and overlapping craters, especially if the impacting body breaks up just before hitting, either in reality or in the lab. And in fact, if you use a plaster of Paris meteorite instead of a cement dust meteorite, you can see what happens to the meteorite as it impacts. And you find the meteorite fragments become concentrated under the rim of the crater.
In contrast to the characteristic features of impacts, what are some of the telltale signs that a crater was most likely formed by the process called electrical discharge machining?
Craters formed by this process, electric discharge machining, or EDM, happen when there's a persistent electric current in a lightning-like discharge which excavates or machines out a circular pit. This has been investigated in detail by lab experiments at, for example, the Vemasat laboratories by C.J. Ransom and others. Although electric discharge machining EDM can produce craters that are bowl-shaped, many craters formed by EDM processes have vertical walls and almost flat floors. This is rather like a number of craters on Mercury and Mars. There may or may not be a rim of debris around the EDM crater pit, depending on local conditions. And because of the behavior of electric currents, multiple or overlapping craters can often occur. And so can the scalloping of the crater edges or the wall. Where the current is high, and this is something important too that I noted, where the current is high, the ground in the region around the crater or craters is often discoloured, and you can see this in some locations on Mars. One of the diagnostic features of EDM craters is that they can have a series of ejector blankets on top of each other that looks like a series of fluid flows. You get the one blanket on top of the other, and you get lopes and scarps and so on. This happens as one layer of dust and debris from machining gets added on top of another over a relatively short time. However, it's impossible for this sort of blanket to be formed by more or less instantaneous explosions from an impact, as several different explosions would be needed in a series of events to form the different blankets to a single crater. Instead of radial ridges, the electric currents involved can form a radial system of grooves around the crater. These are a form of Lichtenberg figure machined out by the electric arc. In addition, the dynamics of the process allow for central peaks in craters of any size. You can't do that for impact craters, as well as circular rings in place of the central peak. Where you have circular rings in place of a central peak, these are called peaked rings, and they usually occur in craters with flat floors and vertical walls, and so they probably have an EDM origin rather than impact. For example, the crater Meade on Venus consists of almost vertical walls, several concentric rings, and a flat floor, and is about 175 miles across. And this strongly suggests an EDM origin. some small crater chains can be formed by impact, but the extensive systems on the Moon and Mars rules out any impact origin. In addition, many craters in the chains are connected by flat-floored grooves. The craters themselves usually have flat floors, and some of these small craters even have central peaks. And so this is impossible to form by impact. These characteristics also eliminate volcanism and only leave EDM as their origin. Indeed, if such machining can produce this form of crater chain rather easily, and there are some excellent examples on Mars and the Moon which parallel electrical experiments. So these crater chains are actually evidence of EDM.
We have noted the ability of electrical discharges to produce flat-floored craters. Does this mean that all flat-floored craters on planets and moons are electrical in nature?
No, probably not. For example, there are some flat-floored craters on the Moon which border the Great Plains, like Archimedes and Plato around the Mare Imbrium. When their walls are examined, there's evidence that flying debris from the formation of Imbrium itself, when the explosion happened, crashed through these walls. So these craters were there before that Great Plain formed. The material that now covers their floor has the same texture, colour and spectral composition as the material making up the Great Imbrium Plain. So it seems that this originally molten rock that formed the plain has penetrated these craters, filled up the depressions and given them flat floors as a result. So we need to be discerning as we have a look at this issue.
In summary, we asked Barry Setterfield which features he feels are most reliably diagnostic for distinguishing impact craters from those unequivocally associated with electrical discharge machining.
Okay, if we start with impact craters, any or all of the following features would indicate impact has occurred. You've got your overturned rim layers or inverted strata on the rim. You've got array system and or radiating ridges. You have nickel-iron bodies embedded under the rim. You have shock quartz and or an associated iridium or osmiridium anomaly, and a concentration of mass, a mass-con as it's sometimes called, associated with it. Now for EDM, any or all of the following characteristics will determine if the crater has an electric origin. You've got your vertical walls and horizontal rim strata that are not mirror imaged. You've got an ejector blanket system of multiple layers, a central peak if the crater is outside the accepted size range for impact, and then you have a peaked ring system forming the appearance of concentric craters with flat floors and scalloping of crater walls. So all of these criteria would form the basis for determining which craters have formed by either process, unless, of course, new developments in both electric discharge machining or geology come to prove otherwise.
For continuous updates on space news from the electric universe, stay tuned to thunderbolts.info.